guess we could, or I could just drop that and we can go quickly so we can get out of here. Or we could just like sort of stop when people seem like they're sweating a lot. Maybe we'll just do that. Then we'll do a univariate regression. Keep going with that. Talk about measures of fit. How do we tell if our model is good or if it's bad? And then we'll talk about the assumptions we need to do stuff. You don't really need any assumptions to draw lines through dots, but you do need assumptions to make some inference using those lines. All right, clarifications on the homework. Number one, 3D has been changed to clarify some confusion. Either one is right. I don't care. I really, truly don't care. This one. So I moved the parentheses from right around next to it. It says do it however you want. Really do however you want. You'll get there. You can do it two different ways. They give you different answers, but you'll get credit either way. So if you've already downloaded it and completed it, you don't have to start over. That's all. Okay, there are some questions about 1A and 1B. 1A and 1B are correct, but you have to remember something. I'll give you the hint. The sum of xi is the same thing as 1 times the sum of xi, which is the same thing as n over n times the sum of xi, which is the same thing as something else. Let's sort of split those.
Times
1 over n times the sum of xi, which is the same as n times x bar. If you have that, you should be able to do it. Good. There's a request for some practice problems about hypothesis testing. Because we're going to be talking more about that next time, we'll do a little bit of practice in the beginning next time, just some like application, how would you actually do this in the real world, but not today. So I hadn't forgotten about the request, we're just not doing that today. Okay, so it's kind of boring just to talk about econometrics in the abstract, at least it's not satisfying for me. So let's talk about grades and the way you can apply econometrics. This will hopefully, and I'll put this paper on eCampus, you can read it, it's optional. Let's talk about grade inflation. So this is a chart, horizontal axis, years since World War II up through 2008. Vertical axis is percent of graduating, or that's college students receiving each letter grade. So what happens over time? A's were rare, they become much less rare. I assume at this university there was something like this going on. Everyone used to get C's, now a lot of people get A's. So why did this happen? Super interesting history. People didn't want their students going to the Vietnam War, so they would give them higher grades, they wouldn't get drafted, you get the draft deferment. And also, I give you good grades, you give me good reviews, we have this implicit understanding, and that's a good thing for professors to get good reviews. So what happens if a university tries to fight grade inflation? There's a very nice econometrics paper here. You can read it, we'll go through it quickly, and you can see the sort of question you can answer with econometrics. Anyone else like graduates in the room? Nope. Okay, some people go there. Some people have gone to that university and taken my class before, so I was checked. So the average GPA at that university was like 3.5. The university put a cap on GPAs and said that at the department level, your GPA can be no higher than 3.33. So this is what we're going to investigate. What happens when you do that? You can use econometrics to figure it out. So these were the grade deviations, 3.33, across departments. So the larger the number, the more grade inflation you have. The smaller the number, more negative, the less grade inflation. So you can see hard sciences, econ, not a lot of grade inflation. They hand out low grades. Other things, looks like languages and social sciences that aren't econ, handed out higher grades. So the departments that had grade inflation had to lower their grades. That was the rule. Departments that didn't were just allowed to keep on grading. And the question is, how do you estimate these effects? You can use a simple econometric model, and then you can look at all sorts of other things. What happens to grades? What happens to majors? What happens to professor reviews? And what happens to students trying to get jobs? So this is what the econometric model looks like. This will look pretty similar to what we're doing today. So today we'll use like a pretty simple example, but you can do more complicated things. So you can look at student GPA. You can look at the effect of being before or after 2004. You can look at the effect of being in a department that gives high grades or not high grades. And then you can take the product of those two, and that'll tell you what is the effect of trying to fight grade inflation. That coefficient will tell you the policy effect here of telling professors lower grades. And visually, this is what it was. You can estimate this in a regression. You would see that in those departments that gave low grades, there was no effect. You just see the GPA, which is sort of flat over time. The departments that were getting high grades, they could lower their grades. There was a visual effect there. So if you tell me I need to lower my grades in my classes, I can hand out B's as easily as I hand out A's, and that's what happens. So you can use econometrics to estimate this precisely. This is the sort of question you want to answer. And if you read the question, if you read the paper, you see all sorts of other things. So there you go, an example of econometrics. So let's get into univariate regression. We were talking last time about averages, and now let's move into something a little more useful. We can answer lots of different types of questions with regression modeling that we couldn't do just looking at averages. We're still going to be testing things, we're still going to be estimating things, and we're going to think about the properties of those things that we estimate. So for today, the example I want you to keep in mind is class size for Agec 621 and average final exam scores for the class. So that's going to be the example we're just going to carry through with us today. That will be what I will be referring to. So let's just assume some things just so we're all talking about the same idea. So let's just pretend everyone here has to take 621, the whole university. So lots of classes are doing this. There's many classes, some have just a few students, some have hundreds of students, lots of variation in our data. People are randomly choosing the classes. Everyone takes the same final exam scored on a scale of 0 to 100, and we have data. So that's like the toy example we're going to think about today. So we're going to want to know what the effect a change in class size is on average final exam scores for a class. So if we add 3 students, what happens? The exam scores will go up a point, go down a point. What is it? We could just find beta as the change in the test score for the class divided by the change in the class size. So what does it mean if beta equals negative 0.2? In words.
That an increase in the class size will affect negatively the test scores.
An increase of what? 1 student. Right? So it's not just like an abstract thing. Like if I add 1 more student to this class, I would expect on average the final exam score to drop by 0.2. But we have like lots of classes, lots of different things, so it wouldn't cause every single person, just on average an expectation. So we can rearrange this and say the change in class size times beta equals the change in the test score. So now we can have any sort of class size change we want. If we add 1 student, easy enough to interpret, right? Average score goes down by 0.2. What happens if we add 3 students? 3 times negative 0.2 is negative 0.6. So it's easy to interpret, right? We know that the relationship is negative, but if you want to know for a specific number of students what the effect is going to be, you have to multiply through. So right now we are assuming there's this linear relationship between class size and scores. What does that mean in practice? We have 2 students, we add 1 more. It has an effect. If we have 5,000 students, we have 1 more, same effect. That is not plausible, but we're just going to pretend it's true. It's really easy to take that into account and change our model, but if we just have 1 variable, we can't do that. So keep in mind, this assumes linearity, but that isn't it. So that beta coefficient is telling us about the slope of the line. So think about this as we have lots of scores and lots of class sizes. There's this line, we fit the line, let's talk about the slope. We want to know the intercept. So why do we want to know that intercept alpha in addition to the slope? Alpha lets us predict test scores, beta just lets us talk about the change. So this sums it up. If we're interested in this relationship, score is equal to some constant plus that relationship beta times the class size. If we know alpha, we know the average score for a class with no students, which doesn't really make sense. So just think of that as like a class with 1 student and a tutor. So that's like the ideal score. Each additional student we multiply by beta, and we get that effect of adding 1 more student to the class. And if I tell you we are looking at a class of 100 students, what would we expect the score to be on average in that class? It would be alpha plus beta times 100. So each part of that tells you something different. You can keep track of what each of those is going to do. One tells you the effect where x equals 0, one tells you the slope, and taken together, we can make a prediction. Questions? Good. Okay, so we talked before about error turn. There's lots of things that are not in this model that totally matter, right? How good is the teacher? How much does the student study? How available is the teacher for office hours? All that stuff. We could get it, we're not going to get that data right now, we can imagine gathering it, and we're just going to put it in that error term. So what would the data look like? What data would you need to collect? And how would it look in a table if you wanted to estimate this relationship? It looks something like this, right? An individual row would represent a single class. We could just number the classes, right? 1, 2, 3, 4. We would have an average score, and we would have a class size. This is just a notation just to make sure everyone's really clear that when we start doing stuff in Stata, that's how the data are going to look. Rows are observations, columns are variables. We're going quickly to get out of the heat. So what could you tell me if I gave you that data? We've talked about the best linear unbiased estimators, right? So we get alpha and beta. I want you to be able to tell me if that model is any good. Like, be specific, like, does that model describe the data well? And then we want to be able to test some hypothesis about how likely an additional student is to increase or decrease the test score. Are we positive that's going to happen, or is that relationship pretty weak? So those are the things we want to do. Again, estimate alpha and beta. We want to talk about whether or not they are any good, and then test some hypotheses. Okay, so this is the univariate regression problem in the most general form. We've talked about these definitions before. Left-hand side variable is y, that's the dependent variable. Right-hand side variable is x, that is the independent variable. I wrote ui when I meant to write ei, so just pretend that's e. There's a line that comes from estimating alpha and beta, that's the regression line. Alpha is the intercept, beta is the slope. So let's graph this just so we're all very clear on what it is we are estimating in a univariate regression. So final score is on the vertical axis, class size is on the horizontal axis. We will be able to label our points. That could be point x1, y1. This could be x2, y2, x3, y3. Right? This height is the intercept alpha. This slope is beta, rise over run. We divide by 1. In our case, this is negative 0.2, if this length is 1. And what else do we want to see? That's it. So visually, and this line is given to you by alpha plus beta times x. So graphically, that is a regression model. Those are all the pieces. Does anyone have a question about what we're seeing? Now remind yourselves, where does that error come in? That is the difference between the point and the point we predict, that predicted value. So this would be the error for point 2. This would be the error for point 1. And this would be the error for point 3. So it's useful to be able to write down both the equation for this sort of thing, and then to be able to graph, identify in the graph each part of this problem. Yeah? All right, if we're going to be non-technical, error, residual, whatever, I don't care. But if we're going to be like really specific, this is an imaginary model. This is what we think is really going on in truth in the world. Platonic ideal. This is the relationship between x and y. I can never observe this. This just exists out there, philosophically. If I get data on x and y, I can estimate an alpha, I can estimate a beta, and I will have some residual. So that is the error, but what I will estimate is a residual. Just like I can estimate a coefficient, but I don't know that it's the true coefficient. So if I'm being nitpicky, I would say that is an error, we estimate a residual. That's the answer. That is a good question. Other questions? So I never see errors, I only see residuals. Okay, so remember, how do we find this alpha and beta? We want to minimize the sum of squared errors, and that will give us our linear estimator. And that comes by picking values of alpha and beta to minimize this sum. I'm going to show you two proofs. Is it okay if I erase this? No one saying no. I'll give you two proofs. One you've seen before. Actually, the one you've seen before we will skip. Just do what we have. So let's just do a matrix algebra proof for those of you that haven't seen it. The calculus one you saw last week. Because of these unsafe working conditions, we will skip it. Okay. So, if I have some y matrix, y1, all the way to yn. I have some x matrix, and we will think of this as just having n observations of x. But keep in mind, we could actually have x's in there, we could have z's in there, we could have all sorts of different variables in here. So we could actually have as many as we want, and the way we're going to write it, you can have as many independent variables as you want. And the error term is going to be E1 or En. And this is just another way to think about what we're doing. If it is confusing to you, zone out for a minute. This will not be tested, but it's just another way of seeing it that might be useful. So we want to minimize E prime E, which is the same as minimizing the sum of squared errors, which is the same as y minus x beta prime times y minus x beta. These are all the same thing because we are saying the regression model equals y equals x beta plus epsilon. Good? So E prime E is the same thing as y prime y. When I say prime, I mean transpose. Minus B prime x prime y minus y prime x b plus b prime x prime x b. We're just doing the multiplication, but we're using matrices, not scalars. So that would simplify to just rearranging things, y prime y minus 2 y prime x b plus b x prime x b. Grouping our terms together, we can get that. Now we can take the derivative of this with respect to b. That would equal negative 2 x prime y plus 2 x prime x b. We would set that equal to 0 to find the minimum because we want to minimize here. And if x prime x inverse exists, which we assume it does, then E equals x prime x inverse x prime y. And you take the second derivative of that beta function, you should get this, and that needs to be positive definite. Now, some of you might look at that and say, wholly clarified. That really makes a lot of sense. I see what you're doing now. In case it wasn't clear, beta can have lots of rows. Lots of rows of beta. It's not really clarifying. It's okay. I'll give you a moment to look at it. That is the proof.
You said we don't need to know this, right?
But no, but like seriously, it is nice to like think about how you actually do this without using summation. But yeah, you don't have to. It's only done because some people might actually think this is another way to look at it that's useful. And the calculus proof is in last week's Wednesday notes, I think.
Can you step to your right just a little bit?
Oh yeah.
Thank you.
Sure. Thanks for pretty hot stuff. Yeah. I always want to press the next class. Sure. Other question? So E is this error term. So we could estimate this model Actually, we are saying that E prime E is going to equal y minus x beta, right? You're okay if I define E in that way. We are going to suppose a beta exists. It could be that you have data that is collinear. In that case, beta wouldn't exist. We're going to suppose beta exists, and then you're just allowed to solve this. And as long as that inverse exists, beta will exist. So you just need y and x data. B is the unknown, and you can solve for that unknown b. Does that answer your question? Maybe, no? We can discuss more after class, but we will press on unless there's other questions. Yeah?
So, sorry, this is the sum of squared errors?
Yeah, so another way to write the sum of squared errors is we can write all our errors in a matrix, and then multiply those matrices together. And if you minimize this, you will be minimizing the sum of squared errors. If you don't believe me, you could go through the math from the first and second lectures of matrix algebra, and do this, and you would see that this gives you the sum of the errors squared, and then you just need to minimize that. Does that answer it?
Yeah, so just take 2 of x and get our answer.
This is beta. X prime x inverse x prime y. So if you know your x, you know that x matrix, x prime x inverse x prime y, that'll tell you your beta coefficient. So that's the solution. Okay. Let's move on. So these are the solutions. Alpha, that constant term, equals the mean of your y's minus beta times the mean of your x's. And your beta is the sum of y minus its mean, x minus its mean, divided by the sum of x minus its mean squared. Which is another way of saying beta is just the ratio of the covariance to the variance. Covariance of xy over the variance of x. These are all just different ways of writing it. I would expect you to remember these 2 equations. That's probably a good thing to know, the first 2. And why not just remember this one as well? Because it's not that. That would be a good thing to know. That's the OLS coefficients. These are the ordinary least squares coefficients in a univariate model. Now, we can use those estimates to predict, given x, what y will be. So if you give me a class size, and I want to predict their average score, that's going to be alpha that I estimated plus beta times whatever the class size is. The residuals, separate from the errors, as we pointed out, are going to be the difference between the actual y's and that predicted y values. So we can get predicted values from our estimated coefficients, and those predicted values will generate residuals for us, which is the difference between that line and the actual data that we observe. And those residuals account for all that stuff we can't see in our model. How many hours people study? Is the professor any good? Were there lights in the class? Was there air conditioning in the class? All these things that could affect performance, those are in the residuals. Okay, so why are we even doing this? Just take a minute to think. We can do math. It's all very impressive. What's the point of doing regression analysis? So one, it's a cool thing to do. If you're doing economics, if you're doing, I think, sociology, if you're doing finance, most social scientists know what you're talking about. You talk about beta. You're talking about the slope coefficient that describes the relationship between one variable and another variable. So it's the common language. Another thing is you can do this with any software essentially that handles data. Excel can do this. Any SAS, Stata, MATLAB, they're all set up to handle ordinary least squares. And we think the properties are pretty nice. If you want to summarize the relationship between 2 variables, running a regression gives you the best linear unbiased estimator of that relationship. So those are the reasons we're actually doing this. So even though there are really good reasons to do it, it might not actually be useful. So we might have a model that's dumb. So we might regress the final exam score on the number on the door outside the class. Do you think that that would be a good model to run? No, because there would be no relationship between those two. So the model might just be bad, or the effect could be really small. I have colored markers. You could imagine someone not have colored markers. Maybe that helps you guys like a little bit. Like one person, one time will do a little bit better. But that's not a big effect. So if the effects aren't large and measurable, it's not very helpful. Or you can think of another example where you have very noisy data where there's lots of stuff you don't observe, and you're interested in one thing you do observe, the relationship between like a football score and the number of fans. There's just like so much you wouldn't be observing, your model might not be very good. So we're going to talk about ways we can be very specific with that term, not very good. What does it mean to have a model that's not very good? I'm sorry, but I'm going to have to erase this. So intuitively, you understand what it means when a model is not very good. I'm going to draw two models. You can tell me which one is good, which one is not good. Model 1. We're just doing generic x and y, but you can pretend it's class size and score. Model 2. So, which is the good model, which is the bad? Pretend those were drawn with the least squares line. Is model 1 good or model 2, and why? Model 2 is good in words. Why is model 2 good other than the dots are close to the line? There's a response.
That explains the relationship between two variables.
Right. I would say the variation in y is explained very well by the variation in x. As x moves, y moves in lockstep. In this case, x does all sorts of stuff, and y just does other things. They don't seem to be related. So let's make some measures. Those are all like totally right answers. Two ways we can talk about how much of the variation in the dependent variable is explained by variation in the independent variable. R squared and the standard error of the regression. These are similar. We're both kind of going at the same thing, but we're going to measure it differently. So like how good is your model? So R squared is about the fraction of the variance of y that is explained by x. So all you have to do is take the variance of your predicted values and divide them by the variance of your actual data. That's just another way to capture how much of this movement in y corresponds to movement in x. In this case, all of this movement in y is explained by movement in x. You could think of r squared as being the ratio of two things. What we are going to call the explained sum of squares and the total sum of squares. What is the explained sum of squares? The sum of the difference between your predicted values, the average value of y, squared. What's the total sum of squares? The sum of the difference between the observations of y and the mean of y squared. These are just definitions, and the ratio of those two tells you your r squared value. The ratio of the explained sum of squares, the total sum of squares. This is telling you the variance of your data, your sample data variance, or sample variance. And this is telling you about the variance of your predicted values. So how do we interpret r squared? This is just another way to write it. You could note that your observed data is equal to the predicted value plus the error term. And this should be E also, but whatever. I use them interchangeably because it's totally up to you what you call stuff. You can call the sum of squared residuals just the sum of the residuals squared, and then the r squared is 1 minus the sum of squared residuals divided by the total sum of squares. So you can do this two different ways. If one of them helps you intuitively, that's great. If neither, you'll still be okay in life. So let's talk about how we interpret this. The way we've written it, r squared can be as low as 0 and as high as 1. What does this 0 mean? A 0 means you have the worst model ever. Your model explains no variation in model. That would be a 0. An R squared of 1 means there is a perfect relationship between your x and y because your predicted values equal the observed data exactly.
Your R squared is 1, you won't have any error there? Or
If your R squared is 1, yeah, your error would be 0 and everything starts breaking down. And you, what was, why, yes. Ooh, yeah, that should definitely be 1. This one should be 0, this one should be 1. They can't both be 0. So R squared of 1, I'll make that change and re-upload. R squared of 1 means your model is perfect. How could you see this? If you go into Stata, if you want to see it practically, you could regress y on y, right? And then you'll see that the output looks kind of funny. I haven't done this. Why would anyone ever do that? But it should give you an R squared of 1, and then everything else is like weird errors because you don't have any error terms because they're all 0, so it wouldn't be that useful. The higher the R squared, the better. In that meaning, the higher the R squared, the more your X variable explains your Y variable. Have you, that have taken econometrics classes, heard people say that R squared does not matter? Yeah, right? So you should just think of it as, it's telling you something, right? R squared is telling you how much that variable explains of the overall variation. In some cases, I am fine if I have a variable that explains some but not all the variation. That's like an okay thing. I assume class size would explain a little bit, and it's sometimes useful to think about. In other cases, if I want to make a prediction, I want my R squared to be very high because I want to explain all the stuff that's going on. So it really just depends. Are you looking for like a policy analysis? You're looking at predictions. R squared is a tool. It is only useful in some settings. Okay, what's the standard error of the regression? It's just an estimator for the standard deviation of the error terms. What does this mean in practice? We want to know how spread out our error terms are. In this example, the error terms are really spread out, right? There's a big gap here, big gaps, big gaps, big gaps between the error term, between the prediction line and the observed values. Here, all of the residuals are very small. There's a small gap between the observed values and that line. So we want to capture this like distance and this spread of your residuals. And this is how you do it. Square your residuals, multiply by 1 over n minus 2, and then take the square root. You could also write that as the sum of squared residuals divided by n minus 2, square root of that line. This is just a different way to measure how well your model fits the data, or how close your observed your observations are to that regression model.
Will we have to like calculate all of these coefficients, or just randomalize them?
I think a reasonable question would be to say something like this on the exam. You estimate a model, your R squared is 0.071, your SER is 14.9. What does that mean? That is a fair thing to do. And I can also give you some data and say, like, estimate those in Stata. You'd have to look up how to do that. But that would be what I'm looking for, just like an understanding of what it means. Let's talk about what these mean. If your R squared is 0.07, it's a percent, so that's 7% of the total variation in your data is explained by, in our case, class size. So that explains some, but not most of the variation. That's probably not great in terms of understanding all the things that affect test scores, but it might be good enough for your purposes. The SER of 14.9, that's pretty big for a 100-point test. That means that there's a lot of variation in your observed data relative to your predicted values. That means you're wrong by a lot on average. Our model will be pretty bad if those are the case. What would a good model look like? R squared of like 0.9 and an SER of, I don't know, 2. Okay, let's wrap it up. So we need to make some assumptions if we're going to go any further in this class. We can draw a line through the points. That's fine, as I said. But we're going to need to do some additional work if we're going to be making inference. 3 assumptions we're going to make, and we'll leave it at this, are the conditional mean of the errors is 0, our data, or IID, there's kurtosis. Very quickly describe what each of these means. So the conditional mean of the errors is 0. What this means is your stuff that you don't put in your model is not correlated with the variable you do include in your model. So as long as you think class size is unrelated to teacher ability, student studying, all that other stuff, then you're okay. If you think that there is a correlation between the stuff you put in the model and the stuff you can't put in your model, then we have a problem. We'll worry about that later. For now, we're assuming there is no correlation between the stuff in the model and the stuff not in the model. It makes sense if you're doing some randomized control trial. Questions? Okay, we're going to assume the data are independently, identically distributed. This isn't a huge assumption to make as long as you think you're drawing some random sample from the population. We think there are hundreds of classes of Agec 621. We're randomly drawing grades and class sizes from that distribution. We're fine. But if we just sample from, say, the engineering department, then that would be a non-random sample and wouldn't have this assumption holding true. Finally, I will draw a graph that explains what this assumption means. You need to have no big outliers, because everything here will break down if you have large outliers. What does that mean? What if I draw, I just have some x and some y here, and I draw my OLS line in pink. If I have a very large outlier, because the board doesn't go up very high, I will just draw it up here. And if we have an outlier up here, what does the new linear regression line look like? It would look something like this. If I drew this high enough, the line would look like this. Because linear regression is very sensitive to outliers. That's problematic because we can describe most of the observations very well, but if we include this one extra observation, we're in trouble. So you're just going to have to assume that you don't have this blue fella here. And if you have big outliers, you have to worry about that. There's ways you can deal with it, but for now we're just going to assume they're not there. Biological processes tend not to have large outliers. Your height, totally fine. Income, especially if you look at hedge fund or venture capital fund owners, very different story. You could have billionaires and then people that make $10 an hour. So if you're looking at income, you might want to really be worried about this. Let's leave it. And this is assumption 3. We'll call assumption 2. Let's leave it here. We'll talk about hypothesis testing next time. And we'll use these assumptions to say some questions.
What is kurtosis?
It's the 4th moment. So we have the mean, first moment, variance, second moment, skewness, third moment, kurtosis is the 4th moment.
That doesn't help.
It's a fun statistical term. Just think of it as like one way to measure how spread out your data is. So if it is very spread out, like you have infinite kurtosis, you have large outliers.